everybody, welcome back to Let's Go Geo. As usual, I'm your field guide Heather, and today we'll be wandering around some quiet, arid parts of Nevada, and we'll be exploring the classic basin and range down to the Mojave. These regions have some fascinating and rather complex geology to check out. There's volcanoes and all kinds of faults and strange rocks and minerals that sometimes can't even be found anywhere else. Now today we find ourselves in a region that is known as Walker Lane, or sometimes referred to as Walker Trough. This region is around the California-Nevada border, and it's famous for having a lot of faults and also a lot of precious metals that have been mined in famous districts like Comstock, Goldfield, all the way down to the Bullfrog Death Valley region. We'll be discussing lots of cool features around this Walker Lane region over the coming weeks. Finally, the fire smoke's dying down. Hopefully it stays this way. It's still pretty hot, but we'll be able to explore lots of cool geology. But today, we're here to discuss one particular thing, and that is that white stuff that you see behind me in the hills. What is that? Those are ash deposits, and it's actually a great place for us to start a discussion about ash as well as the igneous rock known as tuff. So I'm going to go ahead and take a walk up there so we can get a little closer, so we can look at these ash deposits, and maybe we'll be able to sort out some of this terminology, like what is ash, what is tuff. We can see up there, that's where we're headed. They kind of are eroding out pretty interestingly. They're almost making hoodoos up there. Ash is fine pyroclastic material. Basically, it's this fine material that is actually extruded in a volcanic eruption. It can also travel pretty far. Now, this is why we can find ash deposits from the Yellowstone hotspot eruptions all the way into places like Southern California, believe it or not. We can find stuff from the Long Valley Caldera. This is the Bishop Tuff that we've talked about here. Stuff from Mount Mazama, you might know that as Crater Lake, and spewed really far from its source. This stuff can be hundreds of thousands to millions of years old. We can find the ash, though, in all these other states like California and Oregon and Montana, Colorado. All these ash deposits that came from eruptions really far away. And we also get stuff from recent eruptions. Great example, Mount St. Helens eruption in 1980. That was actually a small eruption compared to some of those other ones that I was talking about. A lot of the stuff in this area is about 30 million years old. So we have Miocene ash in Nevada and California. The Yellowstone hotspot, it's not the same as today. We'll talk more about the movement. There was also a lot of other volcanic activity around here. The Long Valley Caldera, that erupted pretty violently 760,000 years ago. So we have lots of ash sources. What volcano? Where did this come from? And what age is this stuff? We got to trek on up here so we can take a closer look. All right, so we're gonna go ahead and leave this guy alone. He's asked that we leave him alone at his home, and I think that's fair. So we'll continue our discussion down here. All right, perfect. Here's a piece of that ash right now in this wash. So how does ash get deposited and turned into the various igneous rocks that we've been talking about? Now's a good time to review the way we classify igneous rocks. So we have extrusive and we have intrusive. If you remember, intrusive includes rocks like granites. We've talked about granite here. And extrusive includes the stuff that extrudes from a volcano. We've talked about a lot of volcanoes here. Those are your extrusive igneous rocks. So stuff like rhyolite, andesite, dacite, and ash, like we said, is the pyroclastic fine debris that comes out. A lot of it tends to be on the silica-rich end of the chemical scale of these igneous rocks. So remember, there's different ways we can classify igneous rocks. We can talk about their physical properties, the grain sizes, the granite versus the rhyolite, and we can talk about their chemical characteristics. Now, granite and rhyolite are really actually quite close chemically when we compare to something like basalt, which is on the other end chemically. That is less silica-rich. This stuff that we're finding here is highly silica-rich. In fact, I just saw a piece right here Look at this. This is super cool. This beautiful little piece here is basically silica gel. So we have a lot of silica content here building up in the rocks as well. And these are just really neat looking. So back to ash. Extrusive material like ash needs a place to deposit in order for it to be preserved, and we find it later as a rock. So places like basins, playas, lakes, these form areas that this material can essentially get trapped in. And it's an area of deposition. Now we have somewhere where this stuff can collect, so it can become a rock later. It might gather in a lake bed, like the stuff from the Florissant fossil beds in Colorado, or the stuff we find from the Green River formations. It also might come flying down as this volcanic debris turns into a tuff. What the heck is a tuff anyway? Tuff is a term for rocks, volcanic rocks, that form from volcanic debris, mainly fine volcanic ash. Whew, it is getting super toasty out, but that's okay. I love bringing you guys these geo trips, and it takes me to some really cool places, just trying to get, access to the different geologic formations and features so that I can show you. And then there's the fun of trying to get the clip so you guys can actually see it and get a good perspective of these geo features. I have been taken to all kinds of cool places. We run into things like bears and snakes, and it's pretty crazy, get bruised up, stuff like that. Even sometimes break my gear. I broke my tripod not long ago, but luckily I got a new tripod and some film gear from Movo Photo, so I've been testing that out in the field. Luckily, because other than that, I've been pretty much having to film like this, trying to find a spot to put the phone or the camera on a rock like that. That's pretty much what I'm left with if I don't have some good film gear. So if you guys want some more behind the scenes background footage, little chats with me, you can see, how I get the content, stuff like that. I talk about localities, all kinds of interesting behind the scenes stuff. You can get that on Patreon. I am on Patreon now. You can find Let's Go Geo, become a patron. And by doing that, you support the channel, you help me out so I can get gear and get to the places and bring you guys these geo adventures. And also, you get access to that behind the scenes stuff. Otherwise, let's get back to today's adventure. Okay, so now we're just a few miles over the mountains from all that tuff we were just looking at. And guess what I'm finding here? Yeah, more tuff. This stuff is everywhere. There are differences in the style of the tuff. I've collected a bunch from my explorations that I've been doing in these surrounding hills. So let's go down and look at some of these examples. All right, so here's my little fun box of volcanic stuff I've been collecting in this region. Look at all these different examples. This is a piece from the last spot we were at. This is obviously lighter and really looks like a pile of ash. And then we have some other hues, some pinkish hues and other examples here. Now, there is variety in tuff, as you can see from these examples. This piece from the last spot that we were at, this is something that would be very silica rich, and we would call this a vitric tuff. But there are other varieties, and you can see here, so there are some greenish hues, and like I said, pinkish hues to whitish hues. There can be grays and different grays to purplish tones in these tuffs, and that just depends on the mineral consistency in them. If they have a lot of fragments in them, we call them a lithic tuff. So basically, tuffs are a consolidation of ash, tephra, and volcanic debris and fragments. And so we pretty much get two main types. We can have an ash fall tuff, which is from that ash fallout, or we can have an ash flow tuff, which is basically from pyroclastic flows. We can also call those ignimbrites. Now, ignimbrite deposits are these poorly sorted mixtures of rock and pumice fragments, maybe some crystals, all in a ground mass background that is volcanic ash. And these tend to be massive. And I mean more in lacking bedding and layering, but also they can be pretty massive deposits. So much so that as the material comes down, it puts so much weight that the interior portion of the ignimbrite can be quite hot. When the interior is so hot, it can actually weld or fuse the rock fragments together such that they form what we call a welded tuff. And when the tuff gets so hot, the fragments of pumice inside will actually get the air squashed out of them, and they become these flattened pieces of pumice that kind of look like flames. So we call them fiamme, which is Italian for flame. Now you can see in this piece of tuff that I have here, those pumice fragments that are included and some of those being flattened out like we just talked about. I'll also put some pictures of some other great examples of fiamme. And one other interesting thing that we get in these types of volcanic environments is, of course, obsidian deposits and another black substance that we've talked about here. It's called vitrifier, and it's also a black glassy substance that forms in those really hot interiors of those ignimbrites. We saw some vitrifier in previous adventures when we checked out the Charlie Brown outcrop in California. If you don't remember that one, check it out. It had some really great examples of this stuff. But we can also find a lot of this stuff just east of here in the Stone Cabin Formation. Okay, so there's one obvious question we need to answer, and it's, where did all this tuff come from here? Well, it turns out it's from a series of calderas that existed in Nevada around 36 to 18 million years ago, and it deposited tons of volcanic ash, tephra, and debris all over this landscape, so that whole mountains literally exist of this. Whew. During the Middle Cenozoic, much of the western and southwestern portions of the United States were covered in volcanic debris, including sheets of ash flow tuff that came from more than 200 source calderas. Cenozoic volcanism is kind of a big deal, not just for here, but all over. We saw from our adventures in Washington those Miocene flood basalts, and now we're seeing these ignimbrite flare-ups that spread silica-rich volcanic content all over the place. And this was all the result of a coastal volcanic arc here. When we look at central Nevada, there was about 6 different eruptive phases, and they were punctuated by some lulls in activity. That helped things build up to these, what we would call super eruptions. These were very voluminous eruptions. The material that was analyzed from central Nevada tended to be mostly calc-alkalic and potassium-rich. Most of the ignimbrites are on the high silica end, with inclusions of phenocrests. They range from the high silica rhyolitic material to lower silica dacite material, characteristic of a subduction zone volcanic arc environment. Altogether, the in-depth analysis showed that the andesitic material represented about 1/10 of the silicic ignimbrite material. Why such a small proportion of basaltic and andesitic material relative to that silicic stuff? Well, the researchers determined that that was the result of unusually thick crust. So wait a minute, why would we even be expecting more relative basalt? And why do I keep mentioning a subduction zone when we're in Nevada? It turns out there actually was a basaltic oceanic plate source, and it was a source of heat and mass that drove those silicic eruptions. But again, the crustal thickness and other factors kept those proportions more on the silicic side. Wait a minute, there was a subduction zone here? Yeah, there actually was. This is actually the location of an oceanic plate subduction zone that is responsible for the ancestral Cascade Mountains. The ancestral Cascade arc formed as early as 45 million years ago, and it ran parallel roughly to the modern arc that we find around British Columbia, Washington, and Oregon. But the southern portion could be found around just east of the Sierra Nevada mountains, or a little east of the California-Nevada border. Okay, great. That's actually pretty interesting, but there's a lot of this stuff out here, so why would we even really care that much about tuff? In the past, it was actually used in building material. It's also really useful for geologists and paleontologists in dating different rock layers because of the isotopes of radioactive zircons contained in the volcanic ash. And there's one other reason why people might be tempted to flock to areas like this. This might look like just a dusty, quiet, rattlesnake-infested desert scape, but believe it or not, hundreds to thousands of people once flocked to live here. And I mean here. This is now a ghost town, and from the looks of it, you're probably thinking more like a ghost desert. There doesn't seem to be much left here. But believe it or not, in 1909, this was the site where thousands of people were crowded and at least hundreds were permanently living here. A closer look reveals material from old buildings, old cans and metal debris, and the remnants from old mining structures. Here's some more of those can piles and metal debris. There's purple glass here, so we know that's very old stuff. It's pretty obvious from all this debris that people were living here. We have pieces of their china that says KT&K China on it. There's also some other pieces, something George Iris, if you know your porcelain. Over here, we have an old horseshoe or mule shoe. Over here, I see some crucibles. So these are broken up, but these would have been used for field assays. So they could have used this to probably mix an interesting mixture of chemicals in there, but it was to determine the value of their ore that they had and try to figure out how much value in precious metals was actually available. Since this mining boom was pretty much around 1909, that's probably when these were from. Well, there doesn't appear to be anyone left now, but why did they come here in the first place? Surely it wasn't all that tough. Actually, the interaction of all this volcanic material, including the silica-rich tuff and the intermediate, in this case, andesite porphyry, led to the deposition of something they really wanted, and it was gold. I mean, there's gold in them there hills. Well, maybe not as much now. When they came here in 1909, historical records indicate that there was practically gold sitting around for them to grab. Luck doesn't seem to be having that for me today. There was also other things that they ended up mining here as well, and that includes, in addition to gold, silver, some lead, there was antimony, bismuth. What about this environment made it so conducive to the deposition of these metals? Now's a good time for us to talk about what happened to this volcanic material after it was deposited. These rocks tend to be pretty porous and permeable, so mineral-rich waters can move through them. That leads to hydrothermal alterations and some cool features. One interesting result of having these porous rocks, this mineral-rich water moving through them, including a lot of iron, are these really cool patterns, including banding and swirls, and sometimes they're rather colorful. And this is sometimes casually referred to as wanderstone, but technically these are called lysogang rings, and it's the result of a chemical separation process. Hydrothermal alterations are the type that we expect around copper porphyry deposits and massive sulfide deposits, and are commonly associated with regions where we have precious metal deposits like gold. Let's head up to one of the larger mines to see if we can take a look at what's going on. There's another prospect. Another one on the hill over there. Pile of cans. We're seeing a lot of this darker rock here. And this is an andesite porphyry. Now, andesite is an extrusive igneous rock, and while it does occur as lava flows, it can also be found as shallow intrusions, which is probably what we had going on here. And these rocks tend to have these darker ferromagnesian phenocrysts that you see here. Andesitic porphyries are common at convergent plate boundary environments. We find these in places like those that have volcanic arcs or subduction zones. Oh, that's quite a view. So we're on a path here. It looks pretty narrow, so I'm thinking maybe it was a donkey path, because it doesn't look like cars made it up here. Here's another mining prospect. Tons of them around here. This will be a good spot for a little break. I see some cool stuff I want to point out. Other alterations to keep in mind are sericitization, which causes the rocks to have kind of a shiny look, a micaceous look. And this is due to the replacement of feldspars with clay minerals. We also see a lot of yellow staining. Yellow tinge on these rocks. What we're seeing a lot of here is the iron oxide limonite. A lot of that yellow staining going on here, and even this cool piece, which is sort of this bumpy botryoidal-like texture common with limonite. There's a strong sulfur smell emitting from this mine. Sulfur is a common constituent found in hot spring and hydrothermal environments. We've talked about sulfur, the mineral, here, where I showed you those examples of those cool yellow crystals. Sulfur is really cool in crystalline form. In this case, sulfur would likely be found in the form of sulfates and sulfides. We'd likely find pyrite, and pyrite is that sort of brassy cubic looking mineral. Sulfur content, especially sulfides, actually plays a really important role in the deposition of metals like gold. Research published in 2010 by researchers Botcharnikov and Linnen actually showed how important this linkage really is. Metals like gold are transported by magma from deep within Earth's mantle to the shallower crust where accessible deposits form. The researchers looked at how the presence of sulfides in the melt, specifically silica-rich melts like what we have here today, impacted the deposition of gold. And what they found was fascinating. They showed that gold solubility in these silicate melts was highest in a narrow window that required the presence of those sulfides. Therefore, the conditions favorable to the transport of gold and likely other noble metals is likely to be found in magma systems above subduction zones and beneath hotspot volcanoes. Well, I hope you enjoyed today's fascinating tour of ancient volcanic arcs, ghost towns, and gold. Stay tuned because I'll be doing a lot more adventures in the Nevada and California backcountry regions. Lots more to come from these mineral belts and some interesting new minerals to look at here as well. Be sure to check me out on Patreon as well, especially if you'd like to support my geoeducation efforts and keep me out here. Otherwise, I'll see you guys on the next adventure here at Let's Go Geo.